Hello. It has been a while. Hopefully this finds you enjoying yourself. I'm going to be talking about integration. I think somewhere along the lines I have missed a few sections in chapter 3, so I shall come back to those at some point, but for the moment I'm just going to plow on with 4.1, which is to do with integration. So integration in our context for complex variables is really going to be about line integrals. So this is you take a path in the complex numbers and you integrate the function over that path. And because we're integrating over a path, the function will look like we're mapping from the real numbers into the complex numbers. So first we consider functions that look like that. So we consider f, a complex numbers, a function from the real numbers into the complex numbers. If t is our variable for the complex numbers, and this is going to be equal to some real portion times some real portion times I, or plus some real portion times I, and the integral between any two particular points in the plane plane real line will just equal the integrals of the real parts. You know how to do real integration, so this tells you integrate the function with respect to time. You just integrate the two individual bits separately. So that's great, and this satisfies all the normal properties that you would expect. So as an example, you should be able to prove that this is true. And you should also take a look at this. This is a statement that we will end up using later on. The absolute value of an integral, of course the integral of a complex valued function will be a complex number. So this is a modulus of a complex number. It's going to be less than or equal to the integral of the absolute value of the function. So this is the modulus of a complex number, so that's real. So this is a real integral, and this is a complex integral, and that's the modulus, which means we're inside the real numbers and we can compare everything. So more generally, this definition is going to be used if we take a function into the complex numbers, which we consider as a path, and then we have a function which goes from the complex numbers into the complex numbers, and we take the integral of f with respect to z here. So we can take the integral from a to b of f of z of t, for example. Now I'm actually going to put in a z dash of t, and I'll claim that this is a parameterization of an integral, which I will denote with a gamma of fz dz, where gamma is the set of z inside the complex numbers such that there exists a t inside a b w, such that z of t equals w. So this gives a path inside the complex plane, and we're taking the integral over that path. So what do I call this a path? We can always draw this inside the complex plane. Z will have some image. So we can integrate over that. Okay, some definitions. A curve in the complex plane is a function into the complex numbers, and as before we can write this as, for example, phi t plus I psi t. Z is simple if for all u and v inside the open interval defining the curve, u not equal to v implies that z of u is not equal to z of v. So in other words, the curve can't cross itself. Z is closed if z of a equals z of b. Z is smooth if phi and psi are smooth real functions. Of course, phi and psi go from the real numbers to the real numbers, so we know what smooth means for them. And a Jordan curve is simple and closed, is a simple and closed curve. So here's some examples. A, B, C, D. So simple, not simple, closed, not closed, right. A is not simple, but it is closed. Not simple, closed, A. B is not closed, but it is simple. C is closed and simple, and D is not closed and not simple. Some examples. So this is a circle, and if we take z from 0 to 2 pi into the complex numbers, then it's closed and simple. This is a very useful example, and you should think about it, because we'll use it quite a lot. You could also take zt equals a plus reit, which is a circle around a. And another example is zt equals a plus t b minus a and b, complex numbers. So this is a curve that starts at a, and if that's b, it travels directly between them, and it does so between 0 and 1. Important facts that will of course come up at some point. Right, back to it. Definition. A contour is a chain of smooth curves. It's a chain of images of smooth curves. Contour is usually denoted with a gamma. Okay, so what do I mean by this? Well, we know the smooth curve, zi goes from some interval ai in zi goes from ai bi into z. It has an image, gamma I, which is all those z inside the complex numbers, so that z is equal to zit for some t inside AI, BI. This is often just written ZI, AI, BI. What's important to note is the gamma i's don't depend upon the particular curve. There are lots of ways to reparameterize the curve. I could make the interval shorter, and but make the new curve travel along the old curve faster. For example, I could halve this, and I could write this as traveling faster. So for example, I could always write, let me say zi wi2t is equal to zit. Right, and if this will travel over half the distance that the zi would, but because I'm timesing by 2, wi will travel over the same curve. So this is, independent of parameterization, whereas this gives us a particular parameterization of it. So, but it's a chain. So a chain of contours is denoted gamma 1, union gamma 2, union gamma 3, and so on, where Z1, the curve that defines gamma 1, B1, the end of Z1, is equal to the beginning of Z2. And the end of Z2 is equal to the beginning of Z3, whatever the Z1, Z2, and Z3 are. What's important is that in the plane, the bits that make up the curve are connected to each other. So this would be gamma 1, this portion here would be gamma 2, and this portion here would be gamma 3. Gamma 1 ends over here, so that's Z1, B1. Gamma 2 starts over here, so that's Z2, A2. Gamma 2 ends at this point, so that's Z2, B2. And gamma 3 starts there, Z3, A3. Don't get too hung up on which curves correspond to which contours, because that might very well change. But anyway, so that's what a contour is. Right, definition. So given gamma, a contour, the image of the curve z, a, b goes to m, you define the integral over gamma of our function f of z dz to be equal to the integral from a to b. And here I perform a change of parameters. Sorry, not m, complex numbers. So here I perform a change of parameters. Z maps into the complex numbers, and I want to take an integral over the complex numbers. This is kind of a two-dimensional thing, except we're restricted to the set gamma. Z, the image of Z, gives us gamma, so we can reparameterize with respect to t, which is the parameter that Z has considered inside R. So this is using the normal rules for reparameterization, where I'm considering that so a small change in t along the curve gives me a small change of the z's that are defined by the gamma. And given a contour, gamma equal to gamma 1, union gamma 2, union gamma 3, union all the way up to gamma n, we can define the integral of the function over gamma as the sum of the integrals over each of the individual bits. Now, if you stare at the definition long enough, you'll realize that we get all the normal sorts of results that you would expect, and the sorts of manipulations that you'd normally be used to dealing with. Here's an example. Z given by z of t equals t, so this is minus 1 to 1. So the complex plane, that's gamma. Then the integral over gamma, I'm going to call this gamma 1 for reasons that will become clearer in the future, of the real part of z dz is going to be the integral from minus 1 to 1. The real part of z is t, so that's just t, and z dash dt equals 1, so that's dt. This is t squared over 2 minus 1 to 1, which is equal to 0. So important to note, we could change the curve that we used here to define the contour. So we could also take z from minus pi over 2 to pi over 2 into the complex numbers, and we could define zt to be equal to sine t. And when you work it out, this goes from minus 1 to 1. Same contour, gamma 1. So what happens when we take the integral over the same contour for the same function? Well, the real part of zt is still sine t. Of course, now when we take the derivative of t, we get cos of t. So this is sine t cos t dt. And after a little bit of thought, you'll see that this is sine squared t over a half, from minus pi over 2 to pi over 2. And when you do that calculation, you'll see that it's also 0. That is not a coincidence. So let f from the complex numbers into the complex numbers be continuous on gamma equal to z a b for some curve z. Suppose that there exists phi from alpha b into a b, and this has to have which has a piecewise continuous positive derivative. So these are the usual conditions for a change of parameter. We will define a new curve . This curve will go from alpha or beta into gamma, and this will be defined by zeta of t is equal to z of phi of t. Then gamma is also equal to zeta of alpha beta, and the integral from a to b of f of z t, z dash of t dt will also be equal to alpha beta f zeta t zeta of t dt. That's just the normal change of parameter results for the real line, so don't worry too much about that. Definition: if gamma is a contour given by the curve z going from a to b into the complex numbers, then the contour minus gamma is given by zeta from minus b to minus a into the complex numbers, defined by zeta of t equals z minus t. So that just means we travel backwards along the curve. That's all we're doing, traveling backwards along the curve. If we have a contour gamma equal to gamma 1 union gamma 2, then minus gamma is equal to minus gamma 2 union minus gamma 1. And that's because we have to flip these around because we have to change the start and end points. So let gamma be a contour, and f continuous on gamma, then the integral of minus gamma fz dz is going to be equal to minus gamma. So in other words, traveling backwards along the curve changes the sign of the integral, and the proof is pretty easy. It's an exercise in the change of coordinates. So integral minus gamma f of z dz is equal to the integral of minus beta to minus a f zeta t dash t, and this is going to be equal to minus b minus a f zeta minus t zeta dash minus t dt, and this is equal to minus the integral from b to a f of z of t z dash of t with a minus sign around the dt. The minus signs cancel, but we're going the wrong direction, so when you flip it around, so you're going from a to b, you get the required negative sign. Work through the details. In particular, work out what the derivative of zeta is with respect to z. Very good, and that was, yeah, enjoy. Okay, so now a longer example to give you some idea of how more detailed thing would be worked out. Is minus 1, this to 1. This is my gamma 1 that I had before, and I'm going to say that gamma 1 is equal to the image of z1 minus 1 to 1, where z1 t equals t. And then I'm going to take I here, and I'm going to let this be a semicircle, traveling this way, because I go from minus 1 to 1, and then I'm going to travel this way, and it's going to be gamma 2. So gamma 2 is going to be equal to z2 from 0 to pi over 2, and z2 of t will equal ei of t. And then I'm going to take this path over here, gamma 3. Gamma 3 is going to be equal to the image of z3 from 0 to 1, and z3 is going to be equal to minus 1 plus t I plus 1. So importantly, z1 dash of t equals 1, z2 dash of t equals I ei t, and z3 dash of t equals I plus 1. So I can calculate the integral of each of these components themselves. So I already know the integral of gamma 1 because we did that before, but we'll go through it again. The real part of z dz equals the integral from minus 1 to 1. Z of t is just t, and because we have a 1, this is dt, which is equal to t squared over t from minus 1 to 1, which is equal to 0. The integral of gamma 2, the real part of z dz, is equal to the integral from 0 to 2 pi, 0 pi over 2 of the real part of this. So the real part of this is cos of t, and then times by the derivative, which is I e I t dt. So you can expand this out, times the products through, and then work out what the integrals are for the real and imaginary parts. So if you do this, what you end up with is that the integral goes from 0 to pi over 2 minus 1/2 sine 2t plus I times 1/2 cos 2t plus 1/2 dt. Just expand this out, multiply through, work out what the answer is. So this is cos 2t over 4 plus I sine 2t over 4 plus I t over 2 from 0 pi over 2, and that is equal to minus 1/2 plus I pi over 4. And what page am I up to? I don't know, 6 or something, right? The integral over gamma 3, the real part of z dz, is going to equal 0. The integral from 0 to 1 of the real part of z3 times z3 dash t dt, and this is the integral from 0 to 1 of t minus 1 times I plus 1 dt, and this will be I plus 1 t squared over 2 minus t, 0 to 1, which is equal to minus 1/2 minus 1/2 I. I think even though we know that the integral over a contour is path independent, this demonstrates that the integral of a function on a contour between 2 points might not be contour integrated. So what do I mean? Here's minus 1, there's 1, there's I. What I've shown, gamma 1, gamma 2, gamma 3, is that the integral over gamma 1 union gamma 2 of the real part of z dz is not equal to the integral over gamma 3 of the real part of z dz. In other words, the path that you take between 2 points in the plane might produce a different number depending upon what you're integrating. So this is something that actually has an important consequence that we'll see a little bit later on. We can also work out the integral going the other way, gamma 1, gamma 2, and then back gamma 3. What's the integral around the circle? So this is the integral over gamma 1 union gamma 2 union minus gamma 3 of the real part z dz, and this is going to equal the integral of gamma 1 real part of z dz plus the integral of gamma 2 the real part of z dz minus the integral of gamma 3 real part of z dz, and when you plug everything in, what you get is I pi plus 1 over 2. Okay, so I just need to give you a definition at this point. A subset of the complex numbers is connected if for all z and w inside the subset there exists a contour. Excuse me. Excuse me. A contour gamma from z to w, so that gamma is a subset of D. So in other words, you have to be able to draw a path from Z to W inside D. Seems fine. And D is a domain if it is open and connected, which is not really much of a restriction, and domains look and behave a little bit like open intervals in the real line. Right. Sorry, lemma. let D be a domain. Definition. Let D be a domain. We'll let Z0, Z1 be inside D. Let gamma 1 and gamma 2 be contours from Z1 to Z, from Z0 to Z2, so that gamma 1 is not equal to gamma 2. The contour integral, maybe I should say this, let gamma 1 be a contour from Z1 to Z2. The contour integral gamma is independent of gamma 1 if for all contours from Z0 to Z1 inside the domain, the integral of gamma 1 f z dz is equal to the integral of gamma 2 f z dz. So I've already shown before that that's not the case for the real part of z, and the particular contours that we're looking at for before. So we know that we have an example where that is not the case. So let f be a function from the complex to the complex, a function f from the complex to the complex, so that f dash of z is equal to f of z is called primitive, or an antiderivative of f in D. And this is for all z inside D, some domain inside the complex numbers. So yeah, antiderivatives. You've seen them before in real analysis, or integrating things. So this brings us to a very important theorem, the fundamental theorem of contour integrals. Fundamental theorem of contour integrals. Suppose that D subset of C is a domain. And that f, a function from C to C, which is continuous, has an antiderivative f, a function from C to C on D. Then the contour integral of f between points in D are path independent, not just parameterization independent, but path independent. And for all z0 and z1 inside D, if gamma is a contour in D from z0 to z1, then the integral over gamma f of z dz is equal to fz1 minus fz2. Right, back to an example. We have the function f from the complex numbers. The complex numbers given by f of z is the real part of z. We have integral from minus 1 to 1. We have a contour integral gamma 1, gamma 2, and a straight line gamma 3. Since the integral over gamma 1 union gamma 2, the real part of z dz is not equal to the integral from gamma 3, real part of z dz, then the real part of z has no antiderivative on a domain that contains gamma 1, gamma 2, gamma 3. We can put that another way, or just give another example. F of z equals 3z squared, and then an antiderivative for this is z cubed, and that of course works on the domain which is all of the complex numbers. Then we know that the integral gamma 1 union gamma 2 of f of z is path independent, so we know that this is exactly equal to z3 from minus 1 to I, which is equal to minus I plus 1. Now this has the, oh, apologies, that's the phone. Right, so in particular, the theorem says that the integral over gamma 3 of fz is also equal to z3 minus 1 I equals minus I plus 1. And you can check this by direct computation, and you should give it a go. Write down what the formulas are and work it out. So for this particular example, this would be gamma 3 fz dz is the integral from 0 to 1 of minus 1 plus t I minus plus 1 cubed I plus 1 dt. Work it out. You should find out that it's equal to the same thing, which is great. And if you don't, then either you or I have made a mistake. So this is an important example. Calculate this. We're going to calculate the same quantity two different ways. Our contour is going to be gamma. This is going to be equal to z 0 to pi for z of t equal reit. R some unspecified positive real number. The integral over gamma of z to the n, I'm not going to specify the n, dz equals the integral from 0 pi reit power of n reit dt, the derivative. So this is equal to I r n plus 1 0 2 pi e I n plus 1 t dt. This has an antiderivative, so we can work that out. This is going to be equal to I r n plus 1 e I n plus 1 t over I n plus 1, the value from 0 to 2 pi, if n is not equal to minus 1. And if n is equal to minus 1, then this is 0, so that's 1, so it's just a t. This will be I r0, so that's just going to be 1, t, 0, 2 pi, if n is equal to minus 1. And so, integral over gamma zn dz is equal to 0 if n is not equal to minus 1. And if it is equal to minus 1, then that's 2 pi I. Great. Or use the antiderivative. So if n is not equal to minus 1, then d dz of z n plus 1 over n plus 1 equals to zn. So the integral over gamma zn dz is equal to the integral from, well, the start point of the curve back to the end point of the curve. And the start point is when z of t, that's 0 of z of t. Z of t is r-e-i-t, so when t equals 0, that's just r. And same thing with 2 pi. Well, that's z n plus 1, n plus 1 evaluated between r and r, so that's 0. Great. Now, if n equals minus 1, we have some problems. d dz log of z equals 1 over z, which is what we want to integrate. But the principal value of z and as we've discussed, this is not differentiable. Over negative real line. Right. So in particular, this means that d dz log z holds on c minus x real numbers, x less than or equal to 0. But our contour involves a negative number at some point, specifically t equals pi, so that gives us a problem. One way to resolve that is to change the parameterization of the contour integral. So now I'm going to define a contour that goes from minus pi plus a very small amount to pi minus a very small amount into the complex numbers. So this starts here, and it's going to travel all the way around to here. And epsilon is meant to be small. Zt is going to be equal to reit. Same parameterization, well, except different domains, so different parameterization. But okay, now it turns out that the integral of gamma z to the minus 1 dz is equal to the limit as epsilon goes to 0 of the integral gamma epsilon. And this is essentially for the same reasons that limits of integrals exist, and you can work with them in the real numbers. So I'm not going to prove that this is the case, and you can assume that that this is fine, at least for gammas where between 2 points. Well, we can work this out. Because this curve lies within the appropriate domain, this is just going to be the antiderivative. So this is log of z rei minus pi plus epsilon rei pi minus epsilon. So this is the limit as epsilon goes to 0 of Well, we plug this into log. We know what that is. This is ln r plus the principal argument, which is I pi minus, or I times principal argument, minus ln r, this is principal log applied to this, plus I minus pi plus epsilon. And that is equal to the limit as epsilon goes to 0. Well, log r will cancel with the log r, and we get I pi minus I pi epsilon, and we get plus I pi. There's a minus, and it's a plus, minus I pi epsilon. So the limit will be 2 pi I, just as we needed. The principal point, the important point I should say here, is that the limit of a gamma is going to be the limit over the gamma epsilons as the epsilon gets close from either side, and that allows us to apply the antiderivative. Okay, so here we have a converse to the fundamental theorem of contour integrals. If f is continuous on the domain and is independent of gamma inside D, a contour from Z0 to Z1 in D, so if f is continuous on D, a contour, a domain, and the integral over gamma is independent of gamma for a contour independent of gamma, a contour from Z1 to from Z0 to Z1 in D for all Z0, Z1 in D, then f has an antiderivative in D. So path independence and antiderivative go hand in hand with each other. Hi. Oh,